To explain color and magnetism in our complex ion exploration challenge, the transition models apply crystal field theory. Okay, so the crystal part in the names comes from the fact that the central metal ion is surrounded by a specific arrangement or pattern of ligands in a 3D structure. So here you can see we have our central metal ion here, and then we have the ligands surrounding it, and it can form those different 3D structures. Okay, so a lot of times that 3D portion is thought of as a crystal lattice because of its structural arrangements, and that's how you kind of get that crystal portion. Now, the field part of the name comes from the fact that when the ligands are actually approaching this metal ion, okay, they actually come with their own electric and magnetic fields that, of course, increase the energy around those orbitals of the metal ion as well. So when these ligands approach the metal ion, the central metal ion, and of course, we're talking about the d orbitals of that central metal ion here, they are going to have an electric field in their immediate vicinity due to their charge. So we know the ligands can come with a negative charge. Okay, so it's going to have its own kind of electrostatic field coming this way towards the central metal ion. This one's also going to have its own, this one, each ligand is going to have its own electric and magnetic field. But also they can have like neutral charges, but create polar covalent bonds. So we know if they do have polar covalent bonds, then they have the ability to have partial positive or partial negative charges. So no matter what, when it comes to an electrical field, you are going to have like a negative field coming from that ligand, kind of giving all of that negative charge. Okay, we also have the d orbitals of the cation portion. So you really are going to have electrostatic attractions between the metal cation here, which is in the center, and then the negative charge on the ligands. And then we cannot forget that each ligand is going to be acting as a Lewis base and donating electrons. And so those electrons that they're donating are going to have a certain motion. They're going to move in different orbitals, and they can spin. They can actually be pointed up or down and have different spins as well. So those interactions of those electrons donated in the coordinate covalent bond here also can contribute to a magnetic field as well. So we're looking at electrostatic attractions that influence the metal, basically central ion, when these ligands start approaching. And so really, since we're talking about the metal central ion, what orbitals are we talking about? We're talking about d orbitals. And so essentially we are saying that when these ligands approach with their electrostatic and of course metal magnetic fields towards that metal ion in the center here, they're going to influence the d orbitals of that central metal ion, causing them to split into different energies. Okay, and that split is going to influence the shape, be influenced by the shape of the complex ion that's formed. So let's get into that a little bit. So of course our focus is going to be the octahedral shape, okay? So we're going to have our metal here. It can form a bond with, of course, these different ligands, and it's going to be 6 ligands that can form a bond with. Now when it comes to crystal field theory and the octahedral shape, and crystal field theory in general, but we're going to focus on the octahedral portion, we are thinking about 2 things. One, we are thinking about orientation. And then 2, we are thinking about the effects of that orientation on the d orbitals. D orbitals of what? The central metal ion. So what about orientation? Well, we know that when the ligands approach, they're going to have their own electric and magnetic fields, okay? That's going to influence the d orbitals of the metal ions. So when they first approach, when you're talking about any kind of orientation here, we kind of first want to basically orient ourselves, right? So we'll get to this one next. Let's focus on orientation. So first, we're going to have our metal ion in the center, and we know this metal ion is going to have 5d orbitals, okay? So there's our 5d orbital. Now, we also know that we're going to have different ligands that are approaching. Of course, there's 6 of them. I'm just showing here. And these ligands are approaching, and they're going to have their own electrical fields or electrostatic charges, and they're also going to have their own magnetic fields, okay? So that's what we're knowing there. And these magnetic and electrical fields are going to influence these 5d orbitals. The question becomes how? Well, guess what? It depends on the shape of these 5d orbitals. So we know they all have the same energy, which we see here, but they also have all different shapes. So this represents one shape, this also represents one shape, and all these 3 also represent other shapes of the d orbitals. We know they're made of different lobes and kind of this cloverleaf shape as well on the x, y, and z axis. So when we're thinking about ligands approaching, we're thinking about ligands approaching from the X, Y, or Z axis, okay? And of course, when they do approach, it depends on how. So if they approach directly towards the lobes of the d orbitals, then they're going to have a specific, thing that they do. If they approach at between the lobes of the different d orbitals, then they're going to do something else. So we're going to talk about two approaches. The first is going to be directly towards the lobes, and then the other orbitals of the five are going to be basically how the ligands approach between the lobes. Now, why would this happen? Well, it's all about repulsion, folks. So we have our ligands. They have their own electric field. Of course, they also have the electrons that they're donating for the Lewis base. So they're coming with a lot of negative energy here. We also have the metal cations that have their own electrons within these different orbitals as well. And so what we have is a lot of repulsion. So these things are going to repel. Okay? So let's think about it. If we have the ligands directly going to be creating direct bonds here with the lobes of the d orbitals, just like we see with this one as well, then the repulsion there is going to be way higher. Versus if we have the ligands making their bonds, these coordinate covalent bonds between the lobes of the d orbitals, then the repulsion is much less. So we actually have a split. We have the ligands can approach directly to the lobes, and then the ligands can approach between the lobes. And so orientation is going to matter. Now let's go ahead and get into how that orientation is going to affect these d orbitals a little bit deeper. Okay, all we've known so far is that we are going to have ligands that are going to orient and approach the d orbitals of the central metal ion a specific way. So we start off with the 5 d orbitals that we see here of the metal ion that have all their different shapes. When the ligand approaches, energy is going to increase in those 5 d orbitals. So this is going to be our energy diagram. Of course, it's going to increase as you see here. Now, again, because we have those ligands approaching with their own electrostatic attractions, meaning negative charges, and their own magnetic fields, they're going to approach the d orbitals in a specific way. So there's going to be certain d orbitals like this one here and this one here that the ligands are going to approach directly towards the lobes of the orbitals. And when that happens, it's going to cause a split in the d orbitals. So these 5 d orbitals are now going to split into 2 for octahedral. They're going to have 2 orbitals here, and they're going to be 3 orbitals here. These 2 orbitals here are going to be higher in energy. Why are they higher in energy? It's because the ligands are directly basically going towards the lobes of those d orbitals here. So they're going to be higher in energy because there's going to be more repulsion. Now, let's also focus on what happens when they're going to be making these metal ligand bonds between the lobes. When they're making bonds between the lobes, those 3 orbitals, which is this one here, this one here, and this one here, are going to be lower in energy, okay? So yes, because they split into 2 different types of energies, we do have different names. So now these 2 orbitals are going to be called the Eg orbitals, and these 3 orbitals are going to be called the T2G orbitals. And of course, this is all for octahedral shape, which is what we focus on. So again, we had our orbitals, we had the ligands approach our d orbitals on the metal ion, causing them to split. If the ligand approached directly on the lobes, they split into higher energy orbitals called Eg. And if the ligand it was to make the metal ligand bond between the lobes, they split into lower energy orbitals called T2G. So kind of how I remember this for myself is I just say Eg orbitals are called elevated. Just think E for elevated because they're higher energy. And then T2G, I just think T for 3. That means 3 out of the 5 orbitals are lower energy and the other 2 have to be the higher energy. So as you can see, we do see a splitting, right? Now we have to kind of add more layers onto that. So before we just said, oh, we have a splitting. Now let's kind of add more layers. We have this splitting and we see this little delta here. So when we have our d orbitals, 1, 2, 3, 4, 5, and they go ahead and split, we have the higher 2 here, our Eg orbitals, and then we have our lower energy orbitals, which are 3 of them, T2G. They actually create an energy difference. So this energy difference is caused by the split. Okay, that split can be called the crystal field effect. And when you have high energy d orbitals and low energy d orbitals, there's going to be that energy difference, like we're saying, between these 2 types of orbitals. And that is called the crystal, put that here, crystal field splitting energy. Okay, splitting energy. Now, a lot of times you will see that delta. Sometimes you'll see that delta O for octahedral. Sometimes you'll see that delta O CT, all because we're focused on how the d orbitals are split for the octahedral shape. If you had other shapes, tetrahedral, square, planar, for example, then the d orbitals will split differently. But this is for octahedral, which is going to be our 6 ligands that we focus on for this course. Okay, folks? So the difference in energy between the two sets of d orbitals result from electrostatic interactions with the surrounding ligands, and this basically makes up our understanding of crystal field theory. And so now, instead of just saying, oh, we have a different d orbitals that are used in bonding, now we're saying, no, we have specific orbitals that are split in energy based on the ligands that are attached to them. And because of this, and because of this overall theory, we're able to see different properties like color and magnetism, all based on whatever complex ions we see. So now we have to continue to add more layers on what we have here. Let's get to it, folks.